Okay, I'm Shelby Schumacher. I'm going to be explaining my draft problem statement for Project Turn-In number 1. The problem goes as follows. Automatic transmission fluid at 80 degrees Celsius is cooled using 50 degrees Celsius air flowing along the oil pan under a car at 100 kilometers per hour. A plastic ZF transmission oil pan is 0.45 by 0.25 meters, 0.001 meters thick, and equipped with 20 straight rectangular fins. Using the adiabatic tip assumption, determine the total heat transfer rate of the fins if the base temperature is 75 degrees Celsius. Then determine the new base temperature of the oil pan in the case of a 5% increase in the airflow due to driving faster. This problem um, will later have values for the thermal conductivity of the oil pan and the heat transfer coefficients for the surrounding air and the hot automatic transmission fluid. Um, I just don't know how to find those yet. Um, so hopefully those are the only values that I need and that it's not like flipped. Um, yeah. And so this is just a general picture of a automatic transmission oil pan. Um, the learning outcomes for this example problem are first, number 5, which is applying the fundamental heat conduction equations. And this is present because we need to use the numerical answer or find the numerical answer for the heat transfer. And then there's also a specific equation for the heat conduction for a fin, and so that equation would be used. And then this is also a one-dimensional steady state with constant k, and so that all falls under the number 5 learning outcome. And then the second one is number 8, using the dimensionalist transport problem groups. I was looking ahead at chapter 7, and I believe, based on like an example, that you can use the Reynolds number and the Nusselt number to find a surface temperature. And so that's how I would go about doing part B of this question, is by finding these values. And that is this problem. Thank you for listening.